Hello, this is Math Reasoning for April 21st. We're starting a new chapter today. It's a chapter on proving technique called mathematical induction. Let's jump right to it. Okay, so this chapter is on this technique called induction, but really the start of this chapter is the set of natural numbers. Remember, natural numbers are these counting numbers starting from 1, so 1, 2, 3, 4, and so on. It is fairly common to define this starting at 0 or starting at 1. So it really depends on the book you're referencing this, but our textbook defines it as 1 and above, not including 0, so that's what we'll stick to. It is very easy to modify the idea of induction. So it starts from 0 or any other number like 7 or whatever. So what is induction? It's an extremely powerful proving technique where you can prove infinitely many statements by doing two things. Right? So working with number systems and proving things, a lot of times we have to prove things that are like there's infinitely many examples of that we can't take care of all at once. So we need some way to generalize and capture the patterns of things. One way to do this is what's called induction. Before we get there, let's work with a definition for natural numbers. There's multiple ways to define natural numbers. Here's one way one might define natural numbers. Okay, the set n of natural numbers is the intersection of all sets S such that it has the following two properties. You include the 1, and if you have an element in this set, then that plus 1 is also in the set. So you have this like smallest element 1, and there's always like a successor, a number that's following it, that's 1 bigger. Now this is a really weird way to define things. It's weird that it's phrased in terms of intersection instead of describing what that set is, which is 1, 2, 3, 4, and so on. It's described as intersection of all sets with this property. You might find this really awkward, but it's a definition that works in a sense that it's equivalent to what you think of natural numbers is. And it's a definition that's easy to check when you're writing a proof. So let's demonstrate that by working with introducing principle of induction as a theorem. Here you go. Okay, so when we have theorems that are named, sometimes we might put that in parentheses to go with the colloquial name that everybody knows it by. Okay, so this is principle of induction. For each natural number n, we let P of n be a mathematical statement. So this is a statement that depends on some parameter n, natural number n. If properties A and B below hold, then for each n, the statement Pn is true. So as long as you check these two things, all of the infinitely many statements P of n will be true. So the first step is to show that P of 1 is true. So the first mathematical statement has to be true. Part B, for any natural number k, if p of k is true, so if it's given that the kth step is true, then its successor, p of k plus 1, is also a true statement. If you have those two things, then p of n has to be true for all natural number n. Let's see the proof of that. Okay, so let's define a set S. S is a set of natural numbers where the p of n is a true statement. Okay, so by definition, we're looking at all n that are natural numbers. So S, just by definition, is a subset of natural numbers. On the other hand, if we have two things true, A and B, so those are these two statements. If P of 1 is true, then 1 belongs to the set S, because P of 1 is true. That's the condition to be in the set S. And we also have that if P of k is true, then P of k plus 1 is true. So if you have an element in the set where it's true, then x plus 1 is true. I'm comparing this against the definition for natural numbers. So natural numbers are is the intersection of all sets that has these two properties. Okay. So because natural numbers is intersection of all of these sets that satisfies those two A and B properties in the definition for natural numbers, it has to contain the natural numbers. But S is a subset of natural numbers, and N is a subset of the set S, so they have to be equal to each other. So therefore, natural number is equal to the set S. So that means that the P of N is true for all natural numbers. I hope that made sense. Before we go any further, so we're going to prove things. We're going to do a couple of examples using this principle of mathematical induction. But before we go further, I need some notation. So this you might have seen in a calculus course or statistics course, but it's possible that you haven't seen it until you're taking this class. So I want to introduce what's called the summation notation. So summation notation is a shorthand for writing lots of additions. So for example, if I have a situation where I want to add all the numbers through 1 through 10, 1 plus 2 plus 3 plus 4 plus, and so on, if I wanted to write that out, that'll take the width of the pages that I'm working with, or if I'm adding 1 through 100, that'll take just enormous amount of space to just write out. So here's another expression that's a shorthand that means the same thing. So summation notation is indicated with that capital sigma. This is a Greek capital letter sigma. It's a Greek S. I know it looks like a capital E, but sigma is the Greek S. On the bottom of the summation symbol, it gives you the starting number that you're going to work with. So there's going to be like a dummy variable. In this case, it's a K. It could be I, J, or X, or any other letter variable. And that is equal to some number that's called the starting index. So K is going to start by 1 and count by 1 all the way up until what's called the ending index on top of the summation notation. So K is going to start from 1, then it's going to be 2, 3, 4, and so on until 10. And what comes on the right-hand side of the summation notation is the actual expression that you're going to be adding. So here, it's just add the k itself. So I'm going to work with k, which is 1, add that to the next value of k is 2. So I'm going to add 1 to 2, and then to 3, and so on until you reach the ending index 10. You do that step, and then you're done. So that's the same thing as the left-hand side here. So this is a fairly simple one, but you could work with more complicated expression on the right-hand side. For example, here's another summation notation. Here, the index variable is again k, but here I don't have to necessarily start at 1. So I could start with 0, I could start with -3, I could start with 7, and then it goes all the way up until some value n. So maybe you want to keep that as a variable, so you can change that later. And the expression we'll be adding is not the k itself, but 2 times k plus 1. So this will count all of the odd positive integers, right? So when k is equal to 0, 2 times 0 plus 1 is equal to 1. So that's the first expression. Sorry, when you square, that would be the first thing. So the first thing you're going to add is 1 squared. When k is equal to 1, 2 times 1 plus 1 is equal to 3, and then you square that. So that's the next thing you add. So 1 squared plus 3 squared plus 5 squared, and so on, all the way up to the nth odd number, 2n plus 1 squared. Okay, so I hope the notation makes sense. All right, so let's do an example of proof by induction, which involves some summation. Okay, so here's an example. For natural number n, the formula 1 plus 2 plus 3 all the way up until n is equal to n times n plus 1 all divided by 2. All right, so let's prove it by mathematical induction. The expression here on the left-hand side, that could be simplified with summation notation. So I might just do that as a first step of the proof. So let Sn be the summation all the way up from 1 to n. So this expression is exactly the same thing as 1 plus 2 plus all the way up until n. And we will prove that that's the same thing as n times n plus 1 all the way all over 2 by induction. So to do induction, you have to check 2 things. Remember, A and B. We want to make sure that the first time n is true. And we also have to check if it's true at a certain point, then the next number is also true. Okay. So let's prove the case of 1. That's sometimes called the base step. So I will label it as such. So you just plug 1 into the formula that's given, right? So if I just add 1, then 1 is the same thing as 1 times 1 plus 1. So 1 times 2, all divided by 2 is equal to 1. So the base step is checked. For the induction step, we want to show that if it's true at step n, then it's also true at step n plus 1. So what you do is assume that the formula holds at any step n, and then you have to somehow use this fact to show that the similar formula holds for n plus 1. So let's do that. Okay, so S of n plus 1 is the sum from 1 through n, and then you add the next number, which is n plus 1. A good reason to rewrite this as these two things added together is because we know that we have this formula for Sn. Right? So it'll be good to rewrite this guy, the next term, in terms of the previous step. Okay, and we assume that the formula holds. So this is going to be replaced with that expression. Okay. And then we're adding the term n plus 1 to it. Okay. So notice, so we have a fraction and then we're adding n plus 1 to it. So we could get a common denominator. So instead of writing n plus 1, I'm going to write it as 2 times n plus 1 divided by 2. Just to get the common denominator. And then now we can add these two things. Notice that both of the terms, the first term and the second term, both have n plus 1 divided by 2 as a factor. So let's factor that out. By distributive property, we could factor that out. And we have n times that and 2 times that. So that simplifies to n plus 2 times n plus 1 over 2. And then from here, you just have to shuffle things around. So you switch the place of n plus 1 and n plus 2, and we get this expression. Now notice this formula that we just got is exactly the formula we wanted to prove for the case of n plus 1. So if you look at this formula and replace n with n plus 1, n will turn into n plus 1 here, and n plus 1 will turn into n plus 1 plus 1, or n plus 2. And the 2 on the bottom is there. Okay, so the summation formula holds for the step of n plus 1. So we did two things. We checked it for case of 1, it works. And if we assume that it works for step n, we can get the formula for step of n plus 1. By the principle of mathematical induction, the formula holds for any natural number whatsoever. Okay. I hope that made sense. So two things that I want to comment on. Number one, this is extremely powerful idea. You just have to check two things, and you got the formula was true for any n whatsoever. So sum from 1 plus 17 is going to be 17 times 18 divided by 2. We proved infinitely many statements. Sometimes this gives you, for some students, it gives you a kind of unsettling feeling that this argument sounds circular. But I assure you, it's not. For example, if you wanted to see that n equals 17 really does hold, well, we know that it holds for case 1. So the formula holds for 1. And induction step, it seems circular because you're assuming what you want to prove at the end, but it only goes forward, right? So we know that it's true for 1. Then if it's true for 1, then this argument shows that it's true for 2. And if it's true for 2, the argument shows for 3, and so on until you reach 17. Right? Any natural number could be reached starting with 1 and looking at the successor enough times. So it is not circular, it only goes forward. Okay, so that's one comment, is that it might take a while until you convince yourself that this really does prove infinitely many statements. One more thing that I wanted to mention is that it feels like cheating because to prove this formula using mathematical induction, it feels like you have to know this magical formula to begin with. So induction itself may not tell you what formula works. So in that sense, it doesn't tell you what the formula is. Like, you could try to look for a formula in different ways, but it feels like you might have to know the formula or some good idea of what it should be before you get it. Okay, so let's try to prove something using induction. So here's what I want you to do. I want you to take out a piece of paper and try to prove the following statement for all n. So, so here's the theorem. Let's say you have a natural number n and you have some base b, which is greater than or equal to 2. Okay. Then for any n, b to the n is strictly larger than n itself. So this seems like an obvious fact because the right-hand side is growing exponentially and left-hand side is growing linearly. But let's prove it using induction. So you need to take 2 steps. First step is to show that it's true for n equals to 1. And then the second step is that if it's true if this holds for step n, then this similar statement with n replaced by n plus 1 is going to be true as well. I've provided you with a proof just from my experience. This hint helps some students get to the right place. So you can keep that in mind. You can ignore it if you want to. So I want you to pause the video and try it out and see if you can do it on your own. If not, I will show you one way to do this in about 5 seconds. So go ahead and try. I hope you've given an honest try. Here's one way to prove that. Okay, so we will prove that n is less than b to the n by induction. So you have to do it in 2 steps. So the base step, 1 is less than 2, we know that. And we know that 2 is less than or equal to b. So chaining those 2 inequalities, we get 1 is less than b. So we had that formula is true for case n equals to 1. Right? We wanted to show that n is less than b to the n, so 1 is less than b to the 1. That's the first step. Let's do the induction step. So for induction step, you take for granted that this is true at step n, and we're going to use this fact to prove a similar formula for n plus 1. Okay, so I want to, instead of n, I want to start with n plus 1. So let's start there. And then here I'm going to use the hint. N plus 1 is less than or equal to n plus n for any natural number n. So I'm going to replace 1 with something that's bigger, possibly bigger, n, and we'll replace that. Well, n plus n is equal to 2n. Okay. And we know that the base b is greater than or equal to 2. So if I take the 2 here and replace it with b, I'll get something that's possibly bigger. So b times n is greater than 2 times n. And then I'm going to use the fact that we know that n is strictly less than b to the n. So if I replace n with b to the n, I get something that's bigger. I could get that by you could get it by taking this inequality and multiplying both sides by positive number b, and then you'll get exactly this. And then b times b to the nth power is same thing as b to the n plus 1, just adding the exponents together. And this chain of inequality gives you that n plus 1 is strictly less than b to the n plus 1. Okay. So I proved a similar formula for the case of n plus 1. Okay, therefore, so we've done the base step, we've done the induction step. Now we know that this inequality holds for all n. I hope that made sense. You have more problem you can practice on homework, but feel free to use the Canvas discussion board and also the Discord channel if you're not quite sure how to use induction. This is going to take a little bit of practice, but I hope everyone can get there soon. All right, so that's it for this this video, and this is gonna be another video later.